buttermaking. For millennia, it has been a cherished art. Over the last 100 years, the diligent work of buttermakers and scientists has gradually converted the art to an exacting science. However, the robustness and flexibility of the basis of the process, batch churning, has meant that the commercial batch churn process remained viable until the late 70s. Long before the final demise of the batch churn, a continuous process for butter manufacture was sought. Conceived in 1937 and developed over the next 30 years, the Fritz continuous process has progressed through 4 generations of continuous machines till today nearly all of New Zealand's butter is made by this process. The Fritz process, although externally simple, is fundamentally complex, efficient operation being a delicate balance of a number of variables. Also, the process is basically inflexible, producing only minor variations on one product, butter. But there is an alternative. At about the same time as Fritz technology was being developed, other approaches were being followed. Of these, the most successful was the Cherry-Burrell golden flow process, commercially established in 1951 in the United States. Although the golden flow process is still in use to this day, a number of problems with it meant that it was not adopted in this country. However, its flexibility appealed to developers at the Dairy Research Institute, who over the course of 20 years' work steadily improved the process until in 1981 the AMMIX process became available for commercial use. Regardless of the type of process used, 4 fundamental steps must occur in order to convert cream to butter. In the Fritz process, crystallizing is achieved in the cream's silos overnight, concentration and phase inversion during the churning process, and moisture dispersion in the working section. However, with lateral thinking, AMMIX approaches these operations in a different order. Concentration is achieved in the cream concentrating separator, phase inversion in the homogenizer, with crystallization and moisture dispersion achieved in the scraped surface heat exchangers and pin workers. In 1981, the Taitapu Central Cooperative Dairy Company decided to install an AMMIX plant. Located in Christchurch City, nearly all of Taitapu's 5,000 tonnes of butter is sold locally. Cream is received at the AMMIX plant from several sources. All cream is plate pasteurized and chilled immediately after separation and prior to tankering. Cream is transferred from the tanker by positive action pump to one of 2 refrigerated holding silos prior to either vacuation of cream or milk fat manufacture. Cream for manufacture into milk fat is preheated by outgoing buttermilk and pasteurized at 85 degrees Celsius for 15 seconds before being cooled to the process temperature of 55 degrees Celsius. All balance tanks in the factories are level controlled by a microprocessor. Pasteurized cream is accurately metered and flow controlled using a micromotion mass flow meter, as the cream is fed to the cream concentrating separator. This large milk separator boosts the milk fat content of the cream from 40 to around 80%. The cream emerges from the separator as plastic cream. This is pumped to a large single-stage homogenizer, operating around 60 to 100 bar, which through high shear inverts the phase from oil droplets in the water to water droplets in oil, as in butter. Note the shiny appearance of the inverted cream with a marked reduction in viscosity. Some of this phase-inverted stream is recycled back to the homogenizer feed tank to seed the incoming plastic cream, so helping phase inversion. The rest is transported to the milk fat concentrator, discharging at 99% milk fat. The milk fat concentrating separator has a specially designed disc stack. And note the distribution holes at the edge of the discs, which allow the production of milk fat essentially free of water because of maximum residence time across the disc. The heavy phase from the milk fat concentrator containing any water and unbroken fat globules is returned to the cream concentrator feed tank. Buttermilk from the cream concentrator is pumped to the buttermilk separator, which separates any excess milk fat and returns this to the cream concentrator feed tank also. Separated buttermilk is regeneratively cooled against incoming raw cream and cooled by chilled water before storage in the buttermilk silo prior to spray drying. The milk fat is then heated to 80 degrees Celsius by hot water and fed to the model VAC 12C vacuator, where undesirable flavors and last traces of moisture are removed. Vacuation as milk fat rather than as cream in the Fritz process permits substantially reduced steam consumption. On exit, the milk fat is cooled by a tepid water set to 40 degrees Celsius before storage ready for blending. Approximately 15% of the raw cream is required as treated cream for blending in the AMMIX process. Raw cream is regeneratively heated using outgoing cream and passed through the VAC 12C vacuator, this being the same unit as previously used in the milk fat portion of the process. In a larger plant, separate vacuators could be justified. After vacuation, the treated cream is cooled to approximately 8 degrees Celsius and transferred to 1 or 2 holding silos to await blending. A slurry of 50% microfine salt and 50% water is made up in the normal way and circulated past the blending table by semi-open impeller water-sealed centrifugal pump. The amount required by the Buttermix blending system is metered by a specially developed salt slurry valve, suitable for Fritz buttermaking as well. Incidentally, this valve is the only item of new equipment in the AMMIX process. All other plant is commercially tried and true, consisting of standard items of food processing equipment. It is only this particular combination that is new. The operator tests the treated cream for total solids. This result is used to determine the ratio of milk fat and cream to be used in the blending. All the milk solids, not fat, most of the water and some of the milk fat in the butter are derived from the blending cream. In addition, the use of cream for blending supplies intact milk fat globules and assists in providing full butter flavor. This figure, along with ratios for milk fat and salt, are entered into the microprocessor for blend control. Milk fat, treated cream and salt slurry flows are very accurately metered and monitored through micromotion mass flow meters with feedback loops to the blend control. The system used is fail-safe. If one stream cannot maintain its ratio, the total blend shuts down. The 3 streams blend through a static mixer and into the mix tank. The now complete butter mix is transferred by centrifugal pump through 100 micron filters to a triplex high-pressure 3-piston feed pump, speed controlled by a variable frequency drive motor through 2 scraped surface heat exchangers in series. These continuously change the butter on the heat exchange surface, assuring very rapid heat transfer, cooling the blend to around 15 degrees Celsius together with mechanical working. Scraped surface heat exchangers consist of a hard chrome barrel with direct refrigeration in the outer annulus and continuously scraped product in the center tube. Scraping action is maintained by centrifugal rotation and pressure-actuated stainless steel scraper blades. This product space is fully flooded at a positive pressure with any forward momentum of the butter caused by the positive action of the triplex feed pump. From the scraped surface heat exchangers, the solidified butter is pumped through a pin worker, where the gentle working action allows time for crystallization and even moisture dispersion to occur while preventing the interlocking of crystals and the formation of a brittle product. In this plant, further cooling and working are applied in 2 more scraped surface heat exchangers reaching temperatures of 4 to 8 degrees Celsius, followed by further pin working and holding time before arrival at the patting machine at around 8 to 10 degrees Celsius. Total residence time is approximately 6 minutes. Any butter in excess of the patting rate, normally 110 to 120 pats per minute, is relieved by the compensating cylinder and returned to the mix tank via melting pipe and a plate heat exchanger. When the patting machine stops for paper changes, the compensating cylinder sends the total production flow through the remelt system to the mix tank, where the level rises and automatically shuts down the incoming blend. The plant continues recycling until patting recommences. The mix tank level drops and the blend system automatically starts. This represents a significant advance over other butter patting systems in which butter holding must be provided. All circuits in the process can be connected to one of 2 recovery tanks used on alternate days for recovering rinses, start and finish of production, etc. On completion of recovery for the day, the tank is decanted and batch pasteurized and cooled under microprocessor control, ready for metering into the milk fat process the following day. Let's look at how the AMMIX process shapes up when compared with the conventional continuous or Fritz process. Firstly, the most important consideration for the manufacturer are considerations of cost. Capital costs for butter making plant depend heavily on such things as hourly throughput, scheduling of cream supplies, scheduling of production, and whether butter is packed in consumer pats or bulk. When costings of Fritz and AMMIX plants have been compared on the same basis, the capital costs of the 2 processes are about the same. For example, the original quotes for the AMMIX plant shown in this film was within 3% of that for a Fritz plant to do the same job. The running costs for the AMMIX process also compare favourably with those for Fritz. Let's compare the areas of the major consumer of steam in either butter making process. The vacuator. In the AMMIX process, 85% of the fat is vacuated in the form of milk fat, which allows the use of much lower steam flow rates. The flavour of the milk fat can be assessed in the plant and adjustments to steam flow made immediately, thus always ensuring the minimum possible treatment necessary to produce the best flavoured butter. It is thus possible using the AMMIX process to halve the steam required for butter making. The electric power requirements of the 2 processes are about the same. Whereas the butter making machine and the refrigeration compressors are the major consumers of power in the Fritz process, those in the AMMIX process are the separators, scraped surface coolers and refrigeration plant. The AMMIX process lends itself well to modern trends in automation and control. Just as a new Fritz plant can run with 3 principal operators, creamer treatment, butter making and the packing machine, so can an AMMIX plant, with 1 operator on the milk fat plant, 1 on the blending chilling operation and 1 on the packing machine. The AMMIX process offers opportunity for yield improvements over Fritz, particularly in the areas of buttermilk fat losses and control of butter composition. Fat contents in buttermilk of less than 0.4% are routinely achievable. One reason for this low fat content is that the cream has not been subjected to homogenizing effect of vacuation prior to buttermilk removal. The process also offers the achievement of near constant moisture and salt contents because the butter making part of the process is based on the blending together of stable ingredients of constant known composition. Of paramount importance to the customer is the quality of the butter made by this process. Butter from this plant has graded consistently and well over the course of 2 seasons. The smooth plastic body has normally been awarded 5 grading points. Flavour, it's constantly good, if perhaps lacking in initial bloom, although further reductions in evacuation intensity may help lift the flavour. The keeping quality of the butter is excellent. The AMMIX process can be used to vary the physical properties of the butter by altering the arrangement and operation of the scraped surface heat exchangers, pin workers and resting tubes. The range of possible variations is currently being studied by the Dairy Research Institute. For example, the butter currently produced from this plant is considered to be more spreadable at all temperatures and noticeably softer at warm room temperatures. Although the economic aspects of the AMMIX process compare favourably with Fritz, economic factors are not the only considerations which will justify the installation of future AMMIX plants. The biggest advantage of AMMIX is its flexibility. In a world with gross surpluses of butter, New Zealand will need to be able to produce other products with its milk fat in order to keep the dairy industry viable. Firstly, the process is ideally suited for both bulk and patted butter. Throughput can be turned down easily to exactly match that of the patting machines, and there is no need for awkward butter transfer systems. Reject damaged pats can be reprocessed immediately and efficiently regardless of the stage of the dairy season. Secondly, the process has already demonstrated its ability to deal with a number of problems which occur in the commercial world of butter making. Butter which has been downgraded because of composition, body or microbiological faults can be reprocessed into top quality product. Thus, Category 5 butter can be made into Category 1 butter. Salted butter can be made into unsalted. Butter containing foreign matter can be filtered. Rather than storing frozen butter until required for patting, it is possible with this process to store refrigerated or frozen anhydrous milk fat. AMF as well as butter can be made in the same plant. Thirdly, the range of alternative products which can be made is infinite. Products with no moisture through to butter-like products with moisture contents as high as 60% can be made. Dairy spreads containing varying quantities of vegetable oils, fractionated or decolorized milk fat are possible. The AMMIX process is already used to produce New Zealand's 9,000 tonnes of export fat mixes, but the possible range of specialized industrial fat products is only just now becoming apparent to the dairy industry.